In this lab, we use a Shack-Cube interferometer to examine aberrations and perform basic fringe analysis. The procedure involves setting up and aligning the system, capturing fringe patterns, and interpreting what those patterns reveal about the optical surface being tested. A Shack-Cube is a type of beam splitter cube made by cementing two right-angle prisms together. One hypotenuse is coated with a partial reflective coating, allowing it to split an incoming beam into two parts, transmitted and reflected. It is commonly used in interferometry and wavefront sensing. The cube splits the incoming beam into two nearly equal parts and directs them along separate paths. These paths can be reflected back, often using mirrors, and when the beams recombine at the cube, they create interference fringes. It is important because it provides a common path interferometer, which makes it less sensitive to vibrations than traditional interferometers. It enables quick, accurate alignment of laser beams. While both the Shack-Cube and the shear plate are used to assess the quality of a laser beam, particularly its collimation and wavefront integrity, they differ significantly in design, function, and sensitivity. A shear plate is a flat optical element, typically with a slight wedge that produces fringes by reflecting light from its front and back surfaces, resulting in a sheared version of the original wavefront. While shear plates are simpler and excellent for quick visual checks of beam collimation, they are generally less sensitive to subtle wavefront distortions than Shack-Cubes and do not provide the same level of quantitative data. Therefore, the Shack-Cube is preferred for high-precision applications, whereas the shear plate is ideal for quick qualitative assessments and alignment tasks.
To begin the experiment, we align the spatial filter to ensure that the output beam is as uniform as possible. Next, we locate the focus spot of the reference beam on the output side of the cube. This spot indicates where the reference beam, reflected by the convex lens inside the cube, converges. Once we locate this spot, we begin aligning the reference testing mirror, which is a short focal length curved mirror, in this case a plano-convex lens. Using an uncoated lens helps balance the beam intensities, producing high contrast fringes since there is a lower percent of light reflected compared to a mirror. We align, defocus, and tilt the system and observe the resulting fringe patterns. Additional aberrations such as spherical aberration or coma become more apparent in this configuration because of the higher contrast. With the plano-convex lens, we first null the fringes. This is done by carefully adjusting the tilt and focus of the reference testing mirror. To achieve null interference, the test mirror must be positioned so that the center of curvature aligns with the center of curvature of the convex lens within the Shack-Cube interferometer. This ensures that the reflected wavefront from the test mirror perfectly overlaps with the reference wavefront, and both beams interfere coherently. In a perfect setup with perfectly spherical surfaces and aligned curvatures, no fringes would be visible. In reality, a few residual fringes remain, and they indicate slight imperfections in the setup or the mirror surface.
Once the system is nulled, we then add defocus to the mirror. In an aberration-free system, defocus introduces concentric circular fringes. As you increase defocus, the number of rings increases, and their spacing and size can be measured to estimate the defocus wavefront error. We saw a lot of asymmetrical rings in our interferograms, which probably is related to some alignment tilt error in our system. After defocus, we add tilt to the mirror. Tilt introduces a linear phase shift across the beam. If no aberrations are present, tilt will produce straight, evenly spaced fringes whose orientation depends on the direction of the tilt. Vertical tilt shifts the fringes horizontally, while horizontal tilt causes vertical displacement. We saw concentric rings still present when applying tilt, which indicates there is still some wavefront curvature from defocus. We also investigate the effect of combining tilt and defocus. In an ideal system, this combination produces asymmetrical fringes that are offset. The number, spacing, and shape of these fringes reveal the magnitude and direction of the optical misalignments or imperfections. Finally, we replace the reference mirror with a long focal length, low aberration mirror. The goal is to adjust the mirror's position and tilt so that its center of curvature aligns with that of the convex lens in the Shack-Cube. When the centers of curvature coincide, the reflected spot from the mirror should overlap with the reference beam's focal point, resulting in visible interference fringes. We repeated the same procedure by adding defocus, tilt, and defocus plus tilt to the system. The fringes were a lot harder to see in this configuration due to the fact that all the light was being reflected back, whereas for the uncoated optic, only 4% of the light was being reflected. We were not able to take as many qualitative observations for the mirror as we ran out of time.
We modeled a Shack-Cube and Zemax using a non-sequential set of elements. Using this configuration, we could model tilt, defocus, spherical aberration, and various combinations in an ideal perfect system. Using the interferograms, we could compare them to the experimental results of our test bench. Comparing simulated defocus to our experiment, we saw that the concentric rings were symmetrical and centered. The spacing between fringes increased as you added more defocus. This is different from our experimental result because we most likely had some residual tilt in our system. The simulated tilt shows straight line fringes with decreasing fringe spacing as the tilt was increased. The experimental tilt had concentric rings in it due to misalignment issues previously mentioned. The simulation defocus and tilt interferograms are probably the closest ones that resemble our experimental results. They both show concentric rings that continuously become more offset as you increase the tilt. This simulation of the Shack-Cube interferometer allows us to view the expected fringe pattern for all different types of aberrations. For example, we also looked at the interferograms when adding spherical aberration with tilt, spherical aberration with tilt, and defocus.
The manifestation of optical aberrations and interferograms varies significantly depending on the type of interferometer used due to the underlying principles of each device. In a Schack-Cube interferometer, we saw defocus appear as a series of concentric circular fringes reminiscent of Newton's rings. This is because Schack-Cubes use a reference beam combined with a test beam, creating a localized fringe pattern that highlights curvature in the wavefront. Coma in Schack-Cube results in asymmetrical distorted rings, while astigmatism might distort the rings into elliptical shapes, indicating a cylindrical component in the wavefront curvature. In contrast, a non-wedge shear plate interferometer produces straight or slightly curved linear fringes as it shears the wavefront laterally and interferes with itself. Defocus manifests as straight, evenly spaced parallel fringes tilted relative to the shearing direction depending on the amount of defocus. Coma produces a saddle-shaped fringe distortion symmetric about the center, while astigmatism introduces a change in fringe spacing along orthogonal directions, revealing different focal powers in X and Y. Spherical aberration appears as increasingly curved fringes toward the edge of the aperture, indicating the wavefront deviates more from a flat plane with radial distance. The wedge shear plate interferometer also creates linear fringe patterns, but the wedge angle introduces a fixed background tilt in the fringe pattern, causing defocused fringes to appear as slightly curved lines that shift depending on whether the wavefront is converging or diverging. The image from the simulation clearly shows how wavefront inside or outside of focus produce opposite curvatures. Coma and astigmatism in this configuration distort the fringes in asymmetrical or orthogonal patterns, while spherical aberration again leads to fringe curvature increasing with radius but superimposed on the wedge-induced tilt. By interpreting fringe patterns, whether they're straight, curved, or contain local anomalies, we gain insight into the quality and shape of the test surface. Understanding how to align the system and analyze these fringes is essential for anyone involved in optical testing, precision manufacturing, or wavefront metrology. We enjoyed being able to compare our experimental results with the simulated results from Zemax.